Bonjour les élèves, hello students. Right, so today we're going to be looking into the new chapter. I'm going to be trying things today. So the video I'm expecting to be long. If you want to chill with me, you're welcome to do that. So let me show you my screens, something interesting to look at. My voice is terrible, so I'm not going to be talking all the time. What do you do first when you get here? Checklist. Yeah, you know what this is. May 12th, May 11 to 15. Dynamics. So we're moving on from kinematics to dynamics. Level up challenge number 1, Newton. Oh, I haven't reviewed any of it. I'm way too busy, so we're just going to dive into it. Okay, we got our checklist. We're happy. Content. Dynamics. Let's go. Newton's law of motion. Let's go. Yeah, right. Welcome to Dynamics. Dynamics is of the sport. Thank you. Did you take a note of this? You should. What is dynamics? So cinematics was the study of movement and moving objects, right? What else can you move? Dynamics is the study of the forces that will cause change in motion, or the forces that cause things to move, and especially move differently, because the forces will accelerate things, and so it will change the movement. Let's read a little further, please. What is this? Download. Okay. Okay. Well, yes. Oh, wait a minute. Can you hear this? Oh, hold up. Can you even hear this? Let me make sure you can. Oh, God. I'm not sure you can hear this. That's no good. Yes. Faster. Yes, number 1. See, drawing. Thank you. So drawing is mandatory. Next. Topics. I didn't make, these are not my notes. I'm just going to go through. Newton's laws of motion. Define a force. Okay. Newton's 3 laws of motions. You have to know them by heart. Like 1, 2, and 3. Define constant velocity, net force. So we know what constant velocity is, right? No acceleration. Net force comes from total of forces. Inertia is the tendency of a body to continue on its path and at its speed, unless we apply force. Motion of objects. It's kind of long to know all this, right? Can we just move on? Find acceleration, of course. Type of force. Distinguish between mass and weight, not the same. Problem solving with weights. Tension force, normal, compare. This is the whole module they're talking about. Free body diagrams, mechanic problems. So we'll be drawing, solve using that Newton's second law, F equals ma. Momentum and impulse. Momentum, impulse. Okay, we'll get back to that if we have time. There's formulas for both. Function of technology, learning guide. Let's take a look at it. It's a big document. Okay, so you can keep some notes here. I like it. That's pretty cool. They've kind of organized the knowledge. Okay. So maybe these are going to be like examples that they show us, and you can like do them here. That's pretty cool. So like if you want to look back on your dynamics module in the future to better understand your future dynamic modules, seems like an interesting resource. Too bad I don't know how to use it. Next. There's only so many minutes. Hey. Okay. So Newton's laws of motion. Force. What causes the motion of objects to change? The force. Simply a push or a pull for us, mostly for everybody. Caused by person, gravity, electrical field, pushing using electrical, like magnets or, yeah, magnets. The force is a vector. It has a magnitude, so an amount, and also a direction. Because you can pull that way or that way or that way. Which is a vector, yeah. Gravity, magnetisms are two natural forces. We've talked about that before. And they all act on this box. Like if there'd be magnets around, if this box would be made out of metal, that would be a force. Even small, it would be a force. Or strong. Gravity is acting on it. He's acting on it. He's acting on it. What's the total? What's the total of that? And that's what we're doing. And it's not really hard, but we have to remember how to make our triangles and add forces together. Mr. Newton. I have no clue what this camera is doing. It was Galileo who first asked what caused. Let's let her talk. So Galileo first asks, what's going on? Right, because it's at a time when religion tells us what's going on, and that the moons and the stars are created by gods, and that they go around the earth, and they are there for purposes which they explain using theology. But Galileo is looking at those, what is going on? Galileo is looking at those stars and he's saying they seem to be moving on their own. And I can actually make an equation that tells us where it's going to be. I don't need someone to tell me where they're going to be. And other astronomers have done this in the past. And you know, after 2,000 years of looking at stars and saying they're moving the same way all the time, why do I need someone to tell me what that means? And so that's part of the understanding that I get from scientific reasoning. So Newton basically understands that mathematically everything goes around. Well, Copernicus, I think, then said, no, they're not going around us, we're going around them. The moon is going around us, and etc. So they've made mathematical sketches, derived formulas, and figured out how far they are, and they're going around the sun, etc. And that was new knowledge. Disruptive also, very disruptive. And Newton says, okay, so we know that they're going around. What's causing that? Wow. So that's where Newton innovated. He developed the mechanic of why they're going around this way and how they're interacting with each other. What makes it so the sun and the earth, the sun causes this kind of motion for the earth. How is it and why is it? Maybe not how, because that's Einstein. And Newton also said, I don't know how, but I know why, or one or the other. And basically made formulas to calculate why or how. Next. Demonstration. A piece of paper will be quickly pulled. What do you think happens in the piece to the piece of rubber? So we pull the paper, rubber falls. Rubber kind of being pulled a little bit by that paper too. The faster you do it, the less it'll be pulled. So what happens? I don't know. You tell me. Not really. Terrible example of Newton's first law. An object, let's read the law. An object with no net force acting on it, which is not the case, remains at rest or moves with constant velocity. This is inertia. You should take a note. So inertia is the first law, I believe, unless I'm probably gonna have to say something new at some point, but if you don't move me, or I don't move myself, I don't move. Or if this object over there is not pushed, it won't move. Now it's best to understand it in the space, because on Earth there's always a force, gravity. But imagine in space, you just put something in space and you let it sit there. So what is it gonna do? Nothing at all. So that's an object with no net force, and it remains at rest. That's his first law, right? Or it moves with constant velocity. So imagine the same object, but this time I give it a little push. This object is going to travel slowly at constant velocity. And he didn't just say that, it came out like that. Just his whole analysis made it so he understood that forces are changing motion, and without forces, there is no change in motion. So that's his first law. So what do you need to write? You need to write what's inside this thing here. This is Newton's first law. Moving on. Well said. Net force. That's a good point. So the first law says an object with no net force, not no force, right? So if if someone's pulling on me on this side and another one's pulling on me on this side with the same force, and let's say they are exactly opposite to each other, one at 0 degrees, 180 degrees. If he pulls 5 and he pulls 5, what's the net force? We've learned to calculate that, right? It would be 0. That is what Newton said. No net force. And that's why the rubber object makes a lot more sense now, because gravity was pulling the object down. The paper was pushing the object up, and the rubber, was not moving. That's a good example. And when he removed the paper, he removed the ability for that paper to push the object up and let gravity pull the object down. And so basically the net force at that point was gravity's minus 9.8 meter per second square per kilogram. And it wasn't opposed. Why don't we write something now? Hold up. Hold up. New page. Show you. Put this down. Technically, technical. Why not? I always draw this to be the object. The object was on a surface. Gravity was pulling it down. The surface was pushing it up, which we call the normal force. The object is not accelerating. And so basically one is the opposite of the other. We'll go back to modeling in a minute. Not easy. Follow me. No. So yeah, the object has like F1. So we'll label that F1. And you can put a little arrow, but there's going to be arrows everywhere, so I'm not going to put them. F1, there's an F2. So it looks like the object is being pulled by two things. It could be magnets. It could be a star, right? It could be a star over here. It could be anything. Two-person, a horse pulling it, I don't know. A car. And there's also a force in this side called F3. So this could be someone else pulling it. It could be another star. It could be another magnet. Right? Could be anything. It could be a person. I just want to show you. So there comes a point where if you add the forces in X, you have F1, F2, and F3. And maybe it becomes 0. Because if this is 2, this is 3, and this would be, so this could be 2 and 3, and this side could be -5. Right? So we're just saying positively directed for these two, and negatively directed, a magnitude of 2, a magnitude of 3, and a magnitude of 5. And if you add them up, it's 0. So the object at that point would not be, it would look like it's not being acted upon, even though it is. But if the forces are equal, then the object, it looks like it is not being affected by anything. And so it looks like it's at rest. Well, first off, it's at rest, and it looks like this doesn't even exist. But it does exist. And that's where the first law kind of talks about. It says, look, if you have forces acting on the object, if the object is not moving, it doesn't mean there's no forces acting on it, right? It means that if there are forces, their net, this is sum of F. If the total of those forces is equal to 0, then that means that the object will not be influenced, and its movement will not change. And so we can have more forces, etc. Notice that I did it in X on the X-axis, and I could do it on the Y-axis, and we will be doing that in this module. Okay. Wait. Next. Inertia. So again, first law is inertia. Tendency to resist changes is called inertia. I don't know if that's the word I would have used. I would have said the tendency for an object to continue its movement. To resist also is the point of view. The more inertia an object has, let's listen to the girl. Thank you. As you can see, my voice is... Hey, what do you think about this, eh? So, this box is harder to push. Is easier to push than this one. Because the object has inertia. It doesn't want to in order to move it, you have to change its position. And that's what inertia is. It's kind of resisting that. And it's really odd that it's the case. Here you can say, well, the friction is causing this. And you'd be right. Most of this is caused by the friction. But it would be the same in space. If you want to move a bigger object, you're going to need more force to move it. And so objects don't like to be moved, if you want. They also don't like to be slowed down. So it's the same idea. If you're trying to stop a car that's rolling, it's got inertia. And it's harder to stop than a baby stroll, that's going down the street. That's easier to stop. But a car, you might don't want to do that. Next. So there are, in terms of quiz, there's definitely something to take here. You see a black word like this, you should have taken a note. You want me to take notes? Back for a minute. Take the notes that we should be taking. Constantly means the object's acceleration is 0. That's a good note. Look, there's black words we need to take notes. Net force is the total of all the forces. Nice. Literally copy and paste 3 things we're going to need on the quiz. Next. Next. So bigger object, more massive object, more inertia required, or it has more inertia. What was that? That's pretty slick. The object is moving currently on this side a little bit, but because it did it so quickly, doesn't experience that too much. It just falls down. Okay, next. So what's the difference? What do you want to show me? That's pretty cool. Okay, water is also going down. Okay, let's read it. In this demonstration, the $5 bill is quickly pulled out from between the 2 bottles, standing end to end. The upper bottle is filled with water. The meter stick is used to remove hoop. Made the pen. Okay, I know, I've seen it. In the first demonstration, the pen had enough inertia to resist the sideways force of the hoop. Right. So the pen didn't fly off with the hoop because it had inertia by being there. The hoop could not move the pen. It didn't have enough force on the pen to move it. And the pen decided to go down. The second, the upper bottle had enough inertia to resist the sideways force of the $5 bill that was pulled under it, right? Why did the bottle not go with the bill? Because the bottle had inertia, not free will. Next. You'll investigate. Okay. I don't. No, no. Don't say that. I pressed Control, and you can click it. Something happened. Bring it. I'm not sure I want to go through all this. It's like a new lab for me, so I just want to explore it, whatever. Interactive. Click on the link, ensure the force and speed checkbox in the upper right corner screen are selected. Click the motion. Force speed checkbox. Okay. Apply a force of 100 Newton to the right of the crate. Watch the speedometer. Let's do that again. Okay, that's pretty cool. Let's do it again. Speed. 500. Oh, that's interesting. The time that it took also is involved here. So let's apply 500 and hold it. So right now he's applying it. Fell. And that's the current speed, max speed. Let's do it again. Click speed. Apply 500 Newton, hold it. Look at that speed meter. Maximum speed. And the object just keeps going at maximum speed. There is no slowing down. Can we stop it? Yes. Now, we're lucky that our guy is Superman. Right. So he's applying force, going the other side. 500 Newton, fell. It's all right. The other guy is on the other side. He's stopping it. You see the speed going? Let me try that again. Applying the force, increasing the speed, going at constant velocity, Newton's first law. Inertia is involved as the person now tries to stop it, reducing the speed. You can try again. Inertia is involved. Let's try pushing that. That's harder to push because inertia is involved. And that's even harder to stop. His feet are on fire right now. And he stopped it, but it kind of, did you see that? It reached 0 and then it went into the negatives. This is negative speed. Let's put another box on top. There we go. There we go. So that's so reaching 0 and going into the positive speeds. You see that? And then as he applies this force in the negative, the object goes into the negative speed. Let's try that again. Positive force, speed increasing positively. A negative force will be reducing a positive speed, right? A negative force affects the speed negatively. That's what we're seeing. Going down 10, 5, 0, minus 5, minus 10, minus 15 meters per second, minus 20, minus 25. So that force is negative, and it's accelerating it in the negative direction, and the speed now is increasing in the negative direction. Great. Thank you very much. We did all that. We just did all that. We did more than that. Because I'm here. Next. Inertial frame of reference. An inertial frame of reference. Okay, play. So we'll just make a quick stop here, I think. I want to know where we are in terms of module. Newton's laws of motion. Initial blah, blah, blah. Okay, so we're almost there. I think we're going fast enough. I'll take a quick break and we'll come back to the other laws. All right, continuing the process of going through the material for this week. Part 2. We'll be looking at the second law, I believe. We're still going through the whole thing. Again, it's kind of my experience going through what you are going through, but also how I would handle it. And hopefully the notes that I've been taking, actually, I put in the OneNote. So here's some notes. And if I wouldn't be doing a video teaching at the same time, I could probably take better notes. There's also some noise all around me. Usual day at work. That's a good discussion. So frame of reference. So the bus is now, so when the ball's put down, it doesn't move. If we push it, it moves. So the frame of reference could be the bus floor. It could also be the observer's frame of reference as they sit here. They can clearly see the ball being pushed by someone else and rolls at constant speed until it reaches the driver. So this frame of reference, or the bus's frame of reference, is valid in the sense that it respects Newton's law. But the second example says, leave a ball on the floor, ask the driver to accelerate, the ball rolls backwards, right, as the ball has inertia. So it's an inertial frame of reference because nobody touched the ball and the ball is now going backwards. So that frame of reference is not a static frame of reference, and it does not respect Newton's law, which doesn't mean they're wrong. It just means the frame of reference is different. If, do you see what I mean? Imagine you put the ball on the floor and someone outside on the sidewalk looks at the ball and the bus is accelerating, right? What does the ball do? Well, if the bus is accelerating, the ball is not moving. For that observer, but the ball is moving for someone who's sitting. And so you can see how those two frames of reference tell different physics. And you could also see how a person that would live on a bus forever would have different laws or physics laws. But the person that lives outside of the bus understands that the bus is moving, the ball is not moving. The ball is not moving. It's got inertia. Okay, so the frame of reference matters in our study. That's all this is saying. So inertial frame of reference, let's go back, is valid. This would not be one, this would be one. This would be an inertial frame of reference. And not this, because the ball is not moving. As it should be. It shouldn't be moving for that person. Check your knowledge, self-assessment. What is a force? A scalar, a vector, a scalar. So it's a vector. Describes a push or pull of an object. Describes the object resistance to change in motion. Resistance is inertia. It's not force. A force is a vector. And it's being like one force. That's what you have to think about. One force pulling on an object. Newton's first law states that an object with no net force acting on it. Let's go check the notes. Remains at rest or moves with constant velocity in a straight line. Okay, the other ones are lacking. 3. What does it mean if an object has no net force acting on it? So no net force means net force 0. Object should not move, should not accelerate, should not change its direction, should not change its velocity. No net force acting on the object. There's no force. No. It's no net zero. Net force 0 doesn't mean that there's no net force. Doesn't mean that there's no force. An object has forces acting on it in the y? No. The total of all the forces acting on it is 0. What is inertia? Tendency to, what is it again? To resist change in motion. Bingo. 5. How does the inertia of a shopping cart full of groceries compare to the inertia of an empty grocery cart? Right, more massive. So more inertia. Empty, more inertia. Wrong. Both have the same amount of inertia. Wrong. Neither shopping carts have inertia. Wrong. The full cart has more inertia. Right. An object that is moving with constant velocity is. So imagine an object moving at constant velocity. It's not experiencing any force because the force would change it. 0 acceleration. We know that. No, I don't want to retake it. Okay, a car is driving down a straight road at a constant velocity. So it's second nature to me to drive. Car constant velocity, acceleration 0. We're going to remove equal and simply state that it's going at v. Acceleration 0. A mosquito. Apologize for my voice. Flying in the opposite direction hits the car. Dude. The mosquito. Okay. Hits the car. So this is a velocity vector, not a force vector. It is flying at opposite direction, unfortunately, for it. Specific reference to Newton's first law explain why the car's motion does not change. Mass 1 is much greater than mass 2. Therefore, the inertia of 1 is also much greater than the inertia. Because if it was a massive object, it would simply change its directions. Because it is much bigger than this inertia, this inertia would win if you want, right? And it's also interesting to note that that is the opening moment, the closing moment, or the before and the after. The after, the mosquito is here with the car in pieces, but remains massive as it was. And the whole is now moving at a constant velocity, which will be super close to the initial velocity of the car, but it will be a little less. How do you say that again? A little less. I don't remember how to say that, but you get my point. And even though it, you can say, well, it's not going to change its speed. The truth is it does, just so small amount that it's imperceivable with the human senses. There's a hint. There's an answer. I gave you my answer. Yay, second law. Copy. Newton's second law. Motion. Simply called the second law. The acceleration of a body is directly proportional to the net force on it and inversely proportional to its mass. Can I write that? The acceleration of a body is directly proportional to the net force, which we can call F net, or also sum of the force, sum of forces. But it's also inversely proportional to the mass. And it's only that. So it's equal. It's wrong. Okay. if you rewrite this, you get this. So if you times by m on both sides, m goes away, it goes over here, ma. Acceleration is a vector, force is a vector, mass is not a vector. So this is interesting. Now, it's not just saying that the force will create an acceleration, but the result of all the forces will create the acceleration. That changes a lot of things. It means we have to draw it, figure out what the net force is, and then we can state the acceleration that is really happening. So one force would create an acceleration. So F1 would create A1. F net, you guessed it, creates A net, or net acceleration. So in other words, if an object experiences F1, F2, and F3, the sum of F, of the forces, is F net, which will create a net acceleration. So let's imagine that this side is a little bigger, whatever. M A net. So if there's three forces acting on this, let's say we put like 3 rockets on a mass and we just start them. Even if this one is a smaller rocket, this is a bigger rocket, this is the bigger rocket, well then the total is going to be a vector. And if you calculate the vector of this, you will get a total in x, a total in y. You'll find the net vector, which will be something like this. This will be F net. And basically we can say, if we know F net to be, for example, 4 Newton in the 210 degrees, then if we know the mass of the object, we can find the acceleration. So we have 4 Newton. Let's say the mass of the object is 1 kilogram. Then you can find A. You don't have to write all of that. There's a lot of writing. You don't need to write it all. It just needs to make sense. So 4 divided by 1 be equal to 4 meter per second square. And the direction will be 210 degrees. So that would be called A net, which is the net acceleration, which is in the same direction as the final vector, naturally. Okay, that was a quick review. Let's go through the material. I don't think I want to do this. You can read this. Acceleration of a body is directly proportional to the net force. The more you push, faster, the more acceleration. Inversely proportional to the mass. If it's a smaller box or a smaller mass, it accelerates more. If it's more massive, it accelerates less. So this is what this is saying. If you increase the net force, you are going to increase the acceleration, right? Say I have 1 meter per second, 1 Newton for 1 kilogram. Okay, so this is the same here. I'm pushing a 1 kilogram object with a force of 1 Newton, it will accelerate it at 1 meter per second squared in space. If you increase this number to 2, you increase this number to 2. You have no choice because it's 2 over 1, which is 2. So that's what I'm doing here. Increase this, you will increase that. That's what it means by directly proportional. Directly means same, more. Proportional means 2, 2, right? And oh, okay. If you increase the mass, you reduce the acceleration. So again, if this is 2 kilograms instead, then your answer is a half, 0.5, not 1. So you've increased the mass, you've reduced the acceleration. That's inversely proportional. So a factor of 2 here, reduce this by a factor of 2, right? But inversely, right? It reduced it instead of increasing it. Increase this, you'll reduce this. And that's not a fact of science, it is a fact of mathematics. This is a fact of mathematics. This is just basic math. It's not physics, but yet it works in nature all the time, everywhere, hopefully forever. Cool. Next slide. A lab. What's up? We're not going to follow procedure. We're simply going to go in. We're just going to see if they want to end, force, speed, okay? And then apply force and see what's up. Which one? Force. Click on the motion. Okay. Apply a force, use a stopwatch. No, we're not using a stopwatch. Reset the simulation. What should we be doing here? F equals ma. They want us to use different forces. And calculate, I suppose, that the acceleration is proportional to the force and inversely proportional to the mass. The time that you apply the force, which is what I'm doing right now, should be the same. And I bet they say that somewhere. Same. No? What about time? Next. I'm good. I'm good. Trust me. You don't need to do this. What are we waiting for? Based on, okay. Results report. That's true. Uh, uh, okay. Next. Problem solving. So here they're pretty sweet. They're telling you the net force already, so you don't have to calculate it and find out using the vector calculation, which you have to be good at uh, normally. They just give you the net force. 300 Newton. They don't even tell you the direction. Accelerates an object at 3.75 meter per second square. What is the mass of the object? You can see that it's clearly just an F equals ma problem. So we're going to use that formula, F equals ma. We're going to write down the four informations. We'll do it. Let's, okay. This is a problem. We read a net force of 300 Newton. You write that down. It doesn't tell you anything else, so it's not a vector. And also it says net, so we should be saying net. Accelerates an object at 3.75 meter per second square. What is the mass of the object? This is the problem. Now, you will solve that problem using the right formula, which is this one. Instinctively, it'll come up. But it's also part of the formulas that we know. I'm not writing that down again. It's right here. Or here. Okay. So what I recommend you do is say m equals f over a. So you can just, so you want m, that's our target right here. So we're dividing by a on both sides. Getting rid of a, we got our target alone. M is f over a. And now we can just put the numbers in. 300 over 3.75. Teachers will ask you to do different things here, like write net, write units. I just find out some of that confusing and unnecessary. But if your teacher is asking you, you should be doing it. Some of you are confused right now because you're like, you didn't ask me to. You're right. So 300 divided by 3.75. 300 divided by 3.75 equals 80. 80 what? Mass kilogram. And this only works if you respect that forces are in newtons, accelerations are in meters per second squared. That's often where the issue is. Okay, this has to be standard. And the mass is in kilograms. Very good example. Could I have, let me try something. No, can't copy that. Well, I could cheese that. Right here. All right. Oh, I don't even need to do that. There's this here, copy and paste. Paint is going to become my next best friend. Next. Solving problems using Newton's second law. So you should be trying these. You don't want to do them all, I understand. You don't need to. You can just try isomorph number 3. 12 Newton force. It's easy. 12 Newton force applied on an object accelerates it at rate of 2.5 meter per second square. What is the mass of the object? If it's a new work, you shouldn't be skipping any steps. This is the formula. This is what we're going to use with the focus, which is m. And then you replace it. Calculator. 12 divided by 2.5. 4.8 kilograms. Final answer. See, this is not hard to find the answer. You don't need to box it because there's one mathematical statement. Or force of 1.38 10 to the 3 Newton. Slows down Twila and her motorcycle. Twila and her motorcycle have a combined mass of 265 kilograms. What acceleration does Twila experience? Oh, by the way. What acceleration does Twila experience? Would you please? You could put vectors, but again, we don't have directions. A is the question. So A would be divided by M on both sides. M cancels out. A is F over M, which is Newton's second law. Could have started with it. Oh, hold up. Oh, never mind. 1.38 times 10 to the 3 divided by 2.65. So what do you do with this? You can't really put that in this calculator. I don't think it takes that. You could, if you know how to, or you can just use your head and move the dot 3 times. 1, 2, 3. This is where the new comma is. There's a 0 here. This would become 1380. After calculation, 520.75 meter per second square. That's the acceleration she would experience. Wait. What do you mean, 2.65? Did I make a mistake? Why did I write 2.65? So 265 is much bigger number. And it's 100 times bigger. That's where our comma goes. Nice. So I assume they're mostly all like this. Let's do the last one. You drop a 5.8 kilogram textbook. The Earth exerts a force that accelerates it towards the Earth's surface as you drop it. The textbooks will exert equal but opposite force on the Earth. If the mass of the Earth, right, so what this is saying is when you drop your book, the book and the Earth attract each other. The Earth being more massive, much more massive, doesn't look like it's moving, but it is, slightly. And we want to know by how much. How much are we accelerating the Earth by? So the book and the Earth are like stuck on each other with something holding them, what am I doing? Let me draw it. The earth and the book are not attracting each other when I'm holding it in my hand, because I'm the one pushing the earth away and I'm pushing the book away from each other. When I'm not there anymore, the book is attracted by the earth is attracted by the book. Mass attract each other. That's how stars and galaxies are formed. That's why your book falls. What's the magnitude of that force? I think that's the question. So let's write down. 5.8 kilogram textbook. By the way, this is problem 10. No, textbooks will exert an equal but opposite force on the earth. That's an important sentence. And the mass of the earth is famously 598, 1024. $598, 1024 kilogram. Acceleration of this book should be g. Acceleration on the book should be minus 9.8 meter per second square, which is g. And are we asking the acceleration of the earth? Yeah. Okay, interesting problem. So what's going on here is that the force attracting the book is equal to the force attracting the earth. Like whenever you have, say you have a negative charge and a positive charge in space, they are attracted to each other. We can ask by how much. And we can also distinguish, we can say by how much is the force, but we can also distinguish that it's this force and this force. Or we can say that F1 is equal to F2. And if we want to be really precise about it, we'll say F1 is equal to minus F2, because this one is going at a positive and this one is going at a negative. Man, what a ruckus. So in other words, this is F1, this is F2, and F1 is equal to negative F2 or F2. You can see where things are going to go. We're trying to work over here. So the first F, I should take my time. Again, I apologize, distractions. MA1 would be then equal to MA2 or M2 M1A1 would be equal to M2A2. Right? Because this sentence says that, but also because they're refreshing your memory. The textbooks will exert an equal but opposite force on the earth. So equal, opposite. So because they say so, I'll put my minus and put the little minus right here. All right. Cool, cool. Let's keep writing. I'm going to bring this down here just because I can't write. Okay, so this is not a new formula. This is simply a concept. The force from that being exerted by the Earth on the book, F1, is equal to the force exerted by the book on the Earth, F2, but opposite direction. So the minus will be helping here. 5.8 times 9, so 5.8 times minus 9.8 is equal to minus this 5.98 times 10 to the 24, sorry, times A2. And it's just an equation, so let's solve it. It's going to be a pain to write on the computer with this. First part, 56.84 equal to minus 5.98 times 10 to the 24. And you see how maybe that's a better example of I didn't move my things before. Like this is the focus. This is our target. I didn't move anything around, which I should have, because now I have to bring all these numbers every time, right? So if you don't mind, I'm gonna scrap that and we're gonna rewrite this. M1A1, which is G, M1G is equal to minus M2A2. This is the focus. So what do we need to do? A2 is being multiplied by minus M2, or we can just say I want to get rid of the minus and I want to get rid of the M2. So how you do that? You divide by minus on both sides. That'll get rid of your minus. And you also divide by M2, right? We could have timed instead by minus. It's the same result. But divide by M2 is necessary. So you end up with this. Let me write A2 first, which is that. And then the minus I'll bring up to the front or on top, because it's better to write that than that. Minus on top, M1G divided by M2. This is not a new formula. We took a concept, they were equal, we're moving things around, we're finding what we need. What was it? 5.8 multiplied by minus 9.8 divided by 5.98 times 10 to the 24. Don't mix up your masses. M1 is 5.8 and M2 is the mass of the Earth. Don't mix that up. Notice how the minus cancel out. So this force is positive, which means it's up. And it's true from our drawing. The Earth, the book was up here and the Earth was being pulled up. 56.84 divided by 5.98 times 10 to the 24. So how do you do this? Well, you have to get a little bit better with this. So this is times 10 to the 0, which means 1, right? I just want to put this out there for a sec. Whenever you have those kind of calculations, it's the easiest thing in the world. You take numbers, you do what you need to do with numbers. So 5684 divided by 5.98. That's 9.5. And you'll notice I kept this 5.6. I didn't write 5.6 because I knew that this would end up with the right amount of numbers before the comma. Because the answer has always one number before the comma. So this will be good. And now for this part right here, you know what to do with this. You know what this is. So 10 to the 0 divided by 10 to the 24, or simply 1 divided by 10 to the 24, or simply moving this up on top, it become minus 24, which we've done last year in math. As you move this on top, the exponent becomes negative. So the negative means that the whole thing goes under. Remember? So this is times 10 to the minus 24. We're done. The answer looks good. We need units because it's an acceleration, and that's it. This is how much the Earth is being accelerated by the book when I let it go. Right? So if I let it go from far, far away, this is the acceleration. And if I give it some time, it'll pick up. The speed will start, the Earth will start moving by that amount. Meter per second. So you will change the velocity of the Earth slightly. Yeah. So everybody go on the same side of the Earth and draw books and see what happens. There's reasons why it's not making our world fall apart. There's other reasons. There's other force at work, right? It's a closed system. Oh, hold up. I want to see my answers. Who's right, huh? Who's right? What's up? Doubt me no more. More problems to practice. John Carr, I don't really want to do them all. This is already taking too long. And finally, the third law of motion. So FYI, the second one is the most voluminous. Good deal. Let's read it. When one object exerts a force on a second object, so an object exerts a force on a second object. The second object exerts a force on the first object that is equal in magnitude, but opposite in directions. Action, reaction. For every action, there is an equal and opposite reaction. You've heard this before. You push on a wall, you're exerting a force. The wall is also exerting a force on you. Doesn't matter if the wall has a brain or not. My wheel. Let me push on the wall like this. Let me shut down my brain. You see me? Okay, I'm shutting down my brain in now. My body is pushing on this. I'm an object pushing on the wall. The wall is pushing back on me, the object. Not a matter of consciousness. It's a matter of reality. At least that's our description. Next. And then you're going to be like, what happens if the wall breaks? Well, then where's the object? Don't overthink it. This law sometimes causes confusion for two reasons. Incorrectly identify action-reaction pair, fail to realize for each force in the pair acts on a different object. Imagine a girl pulling a wagon. The F of the girl, the F of the wagon. The girl pulls on the wagon, and the wagon pulls on the girl. According to Newton's third law, the wagon's pull on the girl is equal in magnitude and opposite in direction to the girl's pull on the wagon, as if we follow Newton. I understand why this is his third law, because he wants to talk, because people need to ask him questions. That's why it's his last law, because then he has time to answer the questions. Why are they not equal? The girl's moving. Well, hold up. She's moving at constant velocity or accelerating, right? Because no acceleration means no net force is zero. So let's see what they say. The forces are equal. Doesn't that mean that there is no motion? Many students would conclude that since the forces are balanced, the wagon won't move. However, this would mean that it would be impossible for the wagon to move at all. Conclusion incorrect. Why? First mistake is to not identify the relevant action-reaction pair in addition to the blah, blah, blah. There is also an action-reaction pair between the wagon and the ground. Yeah, there's friction from the girl's shoes, friction from the wheels of the wagon, pulling back. She's pulling up. Actually, the friction is pulling her back, and the wagon is should be pulling that way. That. Discuss the motion of the wagon. You only need to be concerned with the force acting on the wagon. So we remove the girl, but the forces on the wagon are what? The F from the girl and the friction from the ground. Okay, these two forces are not an action-reaction pair, right? So we had action-reaction pairs. Now we have to ask ourselves, what about the wagon? The wagon has only the force from the girl and the friction from the ground. So the final force for the wagon, not for the system, but for the wagon, will be adding those two together. And the final forces on this girl, made by the wagon and from the ground, will give us the net force for her, but not the system, just hers. Let's read. The girl has two different forces, the force pulling from the wagon back and the force from the ground. It's confusing. As long as the ground can exert more force on the girl, then the wagon will move forward. Situation would be quite different if she was on ice. And if the wagon was more massive. But you can see the interrelation of the variables that we're using. If you increase that m over there, it reduces the force that she can then apply, and the inertia is increasing, etc. It's a whole system. But we normally would we wouldn't talk about two objects like this unless they make up one object. Like, she could sit in it, and then that would be one object. But we normally talk about one object at a time. So this mass, what's happening to this mass? What's happening to this mass? Right. So what I mean by that is this. What's happening to this mass? With the net force, how is it accelerated? Which way is it accelerated? Given that you have just learned about Newton's third law, how does a person walk forward? Give me a hint. So before I read the hint, the friction of your shoes is what makes you go forward. And you could be doing this in space, you wouldn't be going anywhere if you'd be walking in space, right? You only go forward because there's friction. There's something to push, if you want. So there's an action reaction. You're pushing on something, and the reaction is you're moving. I don't know why it's so complex. I don't want to waste time with this. It's a little complex for today. What is that? Knowledge. All right. Newton's second law states that the acceleration of a body is, I don't know, well, let's go check it out. Talk about a question. The acceleration of a body is directly proportional to the net force, inversely proportional to the mass. Directly proportional to the net force, inversely proportional to the mass. All right. If a net force acting towards the west is exerted on an object initially at rest. If a net force, okay, net, acting towards the west, I hope that's the west for you, but I think that's the west for you, is exerted on an object initially at rest. I need to draw this. Object at rest, force to the west. Or V1, or yeah, V1. Which direction does the object start to move? Well, west. A body of mass, M, accelerates under the action of a force. Okay. A body of mass, M, accelerates because there's a force. We'll make it. If a second body requires 3 times as much force, I'm going to do magic. To produce the same acceleration as the first. What is the mass of the secondary body? So we'll call it M1 and M2. So mass is F divided by A. If you have 3F, you have 3M. How can you not, right? We can say F1 and F2, but F2 is also 3F1, right? So, and A could be A1 and A2, but A1, A2 would be equal to A, and they're all equal. So that's why I don't write that. But the masses are different and the forces are different. And you can make a small example like this. Right, and you can say, well, if it's 3 times that, you're starting to see where I'm going with this, then it's 3 times also. There's like 1,000 ways to do this. This is a representation. M1 would be equal to F1 divided by A. That's true. And we can say M2 would be equal to F2 divided by A, or 3F1 divided by A. If you move your tree around, what happens? Oh. If you divide this by 3, and you divide this by 3, you get this. M2 divided by 3 is equal to F1 over A. This is basic algebra. We're just doing algebra. And interestingly, this and this is equal. It is the same, I mean. So if this is the same, then you can say that M1 is equal also to this, because this is equal to this. M2 divided by 3. And again, if you want to know about M2, because that's the question, then you have to isolate this and write, if you do times 3 times 3, get this. 3M1 is M2. So basically, M2 is 3 times M1. And which is what we were kind of saying here. We were saying that maybe M2 is equal to this, but 3M1 would be equal to 3F1 over 8. Right? This is the same. I'm having fun. Let's do another way to do it. A more simple way. In both situations, A equals A. Right? They're the same A's. In this situation, A is F1 over M. And in this situation, A is F2 over M2. Okay. Maybe this is, I like this way better. Personally, that's my personal favorite. And then we can continue extrapolating information. F1 is F1, M1 is M1, F2 is 3F1, and M2 stays M2. Again, we're trying to isolate that because that's the kind of information we want. What happens when you do? So how do you get, so you want to get this back on top. So what you need to do is times by M2, both sides. So you get F1 M2 over M1 is equal to 3F1, because times by M2 divided by M2 cancel out. You would also need at this point to divide by, I would say divide by 3, but what was the question? Was it to isolate F1 or to isolate M2? If a second body requires 3 times, what is the mass of the second body? So M2. So what do we need to do to get rid of all this? Right, we're going to divide everything by F1. Right, that's going to take out the F1 part. And we also need to get rid of the divide by M1. So we're also going to times by M1. You can do these things one at a time, or you can do them at the same time. Let me show you. We are timing by M1 in order to get rid of the M1. Right? So both sides are timed by M1. But we're also dividing by F1. Right? Because we want to get rid of that. So we're dividing by F1. Why am I allowed to do this here and not like here under? I'm allowed to do that. It's the same thing. We're allowed to do that too. Actually, what we did was timing by this, because by experience, I know it's the same. We're also doing it on both sides, so we're not cheating. We're doing something on both sides, it's fine. And naturally, things cancel out. you get M2 is equal to 3F1. Oh, hold up. Canceling out F1s here. That's better. Ta-da. M2 is 3M1. Newton's third law states that when one object exerts a force on a second object, the second object exerts a force on the first object that is equal in magnitude, opposite in direction. The force that the pumpkin exerts on the table and the force that the table exerts on the floor, okay, wait a minute, is the force that the pumpkin exerts on the table and the force that the table exerts on the floor, an action pair? No. 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 A fan hoists a trophy over his head. How does the force exerted by the trophy compare to the force exerted by the fan? They are equal, opposite. $80 kilograms on ice skate, okay, pushes a 40-kilogram boy, also on skates, with a force of 100 Newton. What force does the boy exert on the man? I would say 100 Newton. Although their speed will be different, right? The boy will go faster than the man because the boy was exerted the force of 100 Newton. Man was exerted the force of 100 Newton. They will move at different speeds. Done. No, good. Yeah. What do you want? So I'm not going to be doing this on video. I think you're good for now. Thank you for your time, and I'll be around if you have questions. Again, my pleasure.